the perfect scientific meeting. You know, perfect size, perfect location, great people. You know, so thank you so much. Now, yes, I'm going to. So I really had no idea sort of what was meant here, but yeah, challenging in multi-scale modeling. So okay, so I want to tell you about a few things that we're doing in my group in Iceland. I'm not going to go through all of it, you know, but I'm going to be here throughout the until Wednesday, and so I hope there will be time to sit down and discuss some of these things. I'm going to just mention some of these things. I'm mainly going to talk about two of the, let's say, perhaps the three first items here, okay? Now, first thing I want to talk about is a new way of thinking about and calculating excited electronic states. And what that involves, actually, and Gareth actually mentioned it, we've been working on finding saddle points, you know, basically all my scientific career, but mainly for finding the mechanism and rate of atomic rearrangements, you know, chemical reactions or diffusion events and things like that. Turns out we can now use those same methods with a little bit of an extension to calculate electronic excited states. It's really a surprise, but it really is a opening in terms of both understanding and technology for calculating excited states. Now, we like to actually go beyond cone-sham functionals and do so-called Purdue-Sunger self-interaction correction. I'm not going to talk about that in any great detail. I'm going to basically just show you some results, how to improve by doing the self-interaction correction. But then that's a whole other talk, and I'm perfectly happy to give that at the bar to anyone who is wanting to know more about it. I'm going to talk a little bit about neural networks. I mean, every talk now has to have machine learning for sure. And we are now calculating also electronic states, in particular excited states, with neural networks to accelerate so-called configuration interaction, which is the most exact way of doing electronic structure calculations, okay? So I'm probably only going to very, very briefly mention this, that instead of representing a surface in a calculation with a slab and vacuum on both sides, it's quite a bit better to simulate an semi-infinite solid, actually. And then also once you get to a liquid-solid interface, to have a sort of a hybrid simulation method where you have part of the system is simulated with electrons explicitly, and the other part, the bigger part, just with a potential energy surface. So the application I'm going to mention are the nitrogen vacancy defect in diamond, which is being used for various quantum technologies and is promising even for quantum computing possibly. And then lithium substitutional defect in magnesium oxide. I'm going to talk about some charge transfer excitations in molecules. Of course, molecules are easier to benchmark things with. And then Rydberg excited states. Rydberg excited states are basically where electrons are very, very diffuse. And one could have a similar thing at surfaces, actually, Rydberg states, excited states at surfaces. But here we're going to talk about molecules. Now, bit of a background here. Oh, well, I shouldn't forget. So this is the volcano called Snæfellsjökull. This is taken from basically close to where I live, and I was walking the dog there, the little dog some of us saw here beforehand. This is the mountain where Jules Verne had the journey to the center of the Earth start. They went down the crater here, explored the underworld, and came up in Stromboli in Italy, right? So this is just outside of Reykjavik, yes. I want to mention that we are just about to start a project, and this is what here comes in the Oxford connection, coordinated by Mikhail Stamatakis at Oxford, but then there are these people here involved. This is starting a kickoff on December 1st, and it's going to be a first for us, really, a photochemical reduction of CO2. We've done quite a bit of work on electrocatalytic CO2 reduction, but now we're going to move to photochemical. And so these are all theory groups, and we have an industrial partner here. And we are supposed to work with some experimental group that I think is yet to be determined, you know. But at least this is some new way of doing the funding at the EU. But this system here in particular is going to be the starting focus, which is annotates with copper impurity here and a vacancy next to it. There are amazing reports experimentally about the efficiency of this, namely that CO2 can be reduced not just to form a C2 product, which is sort of the most perhaps exciting thing today, is to form ethylene or something like that, but here they actually form propane, the barbecue gas, and that's amazing. How can you? Sorry? Barbecue gas. Right, well, it's more valuable than methane, all right? And so it's a really remarkable thing, and so that's something we would really like to just focus on. All these groups here will focus on trying to understand this experiment. And of course, we will need help also from experimentalists that really characterize well these surfaces, and who knows what this really looks like. I don't know. I think this is a pie in the sky, okay, in terms of any technological utilization. In my view, I think the only technologically likely thing to happen in CO2 reduction is to make formic acid. Formic acid can now be made almost 100% pure very efficiently, and that's most likely going to be the technology. We very recently actually figured out the mechanism for that. Anyway, so but getting back to the topic, so excited states. Excited states are very often now calculated with so-called time-dependent DFT, time-dependent density functional theory. And usually that's actually done within adiabatic approximation and linear response theory. Why time-dependent DFT? We just want to calculate excited states that are stationary. It has nothing to do with time dependence. Why do people introduce time dependence to calculate stationary states? Sorry?
The ground state problem of DFT. That is a ground state method.
It's a ground state method. That's absolutely right. Yeah. So the functionals and the basic theorem is from ground state. But is there any? So you say any stationary calculation is only going to be good for the ground state, and so time dependence is introduced to get information about the excited states. But the main problem actually is that people didn't know how to not collapse to the ground state. Basically all the tools and mechanisms, the solvers we have, they are such that we minimize or maximize if you multiply by -1. How do you end up staying in an excited state without collapsing to the ground state? Well, that's the key there is to realize that you want to converge onto saddle point. Excited states correspond to saddle points on an electronic energy surface, sort of sketched here. Unfortunately, the colors are a little difficult here, but this is an electronic energy surface. So on the x and y axis here are some electronic expansion coefficients, something you use to represent the wave function. And there's a minimum here that corresponds to the ground state. But then there's a first order saddle point here, and that will correspond to an excited state. These maxima here essentially are second order saddle points in a higher dimensional space, and so correspond to some other excited state. I'm going to illustrate this in a simple example. What I'm talking about here is something that is often, it's under the very broad and general umbrella called delta SCF. Delta SCF simply means that you somehow converge onto an excited state in a time-independent way, and then you get the total energy for that excited state. Now you subtract the energy of the ground state. That's the delta E, and it's the delta of calculating excitation energy. But there are many different methods that are grouped under this umbrella, so be careful about that. These are state-specific calculations, so we converge onto a particular excited state in that calculation. And then if you want to learn more, you have to do more calculations. Now, one has to know what saddle point order you need to go to. It's not always just first order, for sure. I mean, I'm going to show you some examples of sixth order saddle point excited state, for instance. Now, the examples I'm going to show are, it's nice to look at molecules, of course, because we have much more benchmark calculations for molecules. And so I'm going to talk about ethylene, the twisting of the double bond. That's actually the operating system, the operating part of a molecular motor. And charge transfer excitations in molecules, that means that as you excite the system, electrons move from one place to another, and that's typically what you want. If you want to harvest photons, you really want to bring the electrons away so they don't collapse right down to the ground state. And so that charge transfer excitations are very important, of course. Now, as a condensed matter application would be the nitrogen vacancy defect in diamond, which is can be prepared in a pure spin state in an optical way, and then Rydberg excited states. Okay, so let's take an example. Let's just take the simplest example. Hydrogen molecule, 2 atoms, 2 electrons, 2 protons. Instead of, let's put in a minimal basis set, one as atomic orbital on each one of the atoms. But it's easier to work with the molecular orbital, so let's construct the bonding molecular orbital and the antibonding molecular orbital. So instead of working with the atomic orbitals, let's work with the molecular orbitals. That's all we have for a minimal basis set. There's not more than that. But then, of course, we have spin up and spin down. And the ground state, of course, will be having both electrons in the bonding orbital. One will spin up and one will spin down. So we have the antisymmetry here in the spin part and the symmetric spatial part. Now, we can then form in total 4 wave functions because there are 2 molecular orbitals and 2 electrons, spin up and spin down. So, and we can say we're going to put an electron in 2 of those. Let's call those psi1 for alpha spin up, psi1 beta for spin down. And then there will be 2 unoccupied orbitals. And these 4 orbitals, they can be written as a linear combination of the bonding and antibonding with spin up and the bonding and antibonding with spin down. And really, because we're going to conserve normalization, the expansion coefficients are simply sines and cosines. And so we can represent all 4 possible wave functions here just with 2 parameters. That's a phase for spin up and a phase for spin down, phi alpha and the phi beta. So that's nice. Then we can make a contour plot. And we can calculate the expectation value of the energy then for every possible wave function that can be constructed from this basis. And that's basically, the expectation value is going to be a function of these 2 phases, phi alpha and phi beta. So we get this energy surface, sort of like I sketched you before, but now it's a contour plot. And of course, the minimum here for phi alpha equal to 0 and phi beta equal to 0 is the ground state. It corresponds to having both electrons in the bonding molecular orbital. But then we have these first order saddle points, like this one here, where we have phi alpha equal to 90 degrees. So we have then rotated and put the spin up electron into the antibonding molecular orbital. So this saddle point here corresponds to this configuration of the electrons. And then there are, of course, equivalent saddle points like this one here. That means that we put the spin down in the antibonding molecular orbital, and then these 2 here are simply a multiple of -1, so equivalent wave functions. So the first order saddle points here on the energy surface correspond to the first excited state, an open shell singlet. And then we have the second order saddle points, the yellow ones here, and they correspond to having both angles of 90 degrees, and that means we have both electrons in the antibonding molecular orbital. So you can see this connection between saddle points of the energies of the electronic energy surface and the excited states. Now, what you also have, of course, is at these stationary points, you have basically the generalized variational principle fulfilled. The generalized variational principle says that if you have found orbitals such that any infinitesimal change in the orbitals doesn't change the energy, you have a solution of the underlying equations. So you have a solution of the Hartree-Fock equations if you're working with the exact Hamiltonian, or with the Cohen-Sham equations if you're working with a density functional. So these are solutions of the fundamental underlying equations behind this methodology that you're working with. Now let's stretch the bound a bit, and so we can see here the ground state energy surface for the H2 molecule. At some point, you reach this so-called Coulson-Fisher point, and the energy surface changes qualitatively. Look at that. What used to be a minimum at phi alpha and phi beta equal to 0 now becomes a first order saddle point. The so-called Coulson-Fisher point. It's basically saying that if you have a single determinant solution, approximation to your wave function, you better break spin symmetry. Allow for spin up to be in a different region of space than spin down. You don't have an eigenfunction of spin anymore. You're living dangerously. We're breaking symmetry, but you get a lot better energy, right? Otherwise, you climb up in energy. If you stay on this point here, the saddle point, you actually go to way higher energy than the 2 separated hydrogen atoms, right? You get the ionic terms. So this is an example where you want to break symmetry if you are representing the wave function in a single slated determinant. And you want to, stay, and you want to stay at the minimum. So you also have to realize here, you want to stay with the right saddle point order. Okay, here it is 0, the minimum. And basically, if you are now realizing that, hey, suddenly, as I stretch the bond, I'm at the first order saddle point, then say, oops, no, this is not the right solution. I better roll down either to this minimum here or that minimum there, which corresponds to the broken symmetry. So it's another principle of navigating this rather complicated electronic energy surface, that you want to know what saddle point order you should be staying at when you run into these kinds of symmetry breaking points. So the first order saddle point doesn't do much. It's just this repulsive curve here. It's more interesting when you get to the second order saddle point, because there also you can see the as you go past this point here, the energy surface changes in such a way that you don't have a maximum anymore at 9090, for instance. The maximum has moved off, and that second order saddle point has turned into a first order saddle point. So again, realizing you want to stay at the same saddle point order, second order saddle point, you need to move. You need to move out to here. And only that way do you get the proper yellow curve here. Otherwise, you slide down to the ground state energy. So again, it's a key principle to know what saddle point order you should be at when you get your solution. So let's take an example. Let's take the ethylene molecule and start twisting it. And of course, at the same time you twist it, you can pyramidalize this other one here, this one of the carbon atoms. And that's a contour plot here of the energy difference between the ground state and this excited V state. A very important part of photocatalysis, of course, is to find these so-called conical intersections. A conical intersection is where these two electronic surfaces kiss. They kiss at a point here. And this contour plot is showing the energy difference between the two surfaces, right? And so here's the point where they are equal. And the cyan region here is showing where they're within half an electron volt. If you do this calculation, this calculation was done some years ago by these people here with a much more complicated calculation, multi-reference CISD. You can see that this calculation here with a simple PBE functional, this is just a GGA functional, not even a hybrid, it gets this very well. It gets this conical intersection really quite well. And it's quite remarkable. If you, and if you go to linear response time-dependent DFT, it can be shown mathematically you can't get a conical intersection, actually. It just doesn't have that. And you can see how poor it is with B-lip, and then even with B3-lip, you want to improve and get to a hybrid. Well, then the V state actually becomes lower than the ground state here in a certain region. Yes?
Will you include this with the flip?
Yes. Okay. So you can do that. You can add a double excitation. You can do all kinds of things, but basically the way the theory comes, it doesn't work. And this time-independent method actually works very nicely. Now, here is the second excited state, the Z state. And you can see that if we're not careful, again, it says a symmetry breaking point here. If we're not careful, we'll drop down to down here. And that's often a problem with these so-called delta SCF methods, that they don't work very well when you have avoided crossings. But if you follow a second order saddle point, you get this curve. And then we can see the avoided crossing. Here's the ground state, and here's the excited state. Here's the multi-reference CISD calculation with the dashed line. You can see we're underestimating the excitation energy here, the gap, by a bit. But if we do the and then we look at other states. We can look at here the Rydberg state comes in, actually. And you can see that sort of qualitatively, the black line, which is the multi-reference calculation, is actually very similar to the calculation with this just PBE functional using a saddle point search method. But if you use the self-interaction correction, you can see you can almost quantitative agreement with these with the multi-reference calculations. And look at this. This is the Rydberg state that actually comes in lowest. It's actually lower than the V state here. And it comes out properly with the self-interaction correction. It's particularly difficult to get the Rydberg states here without the self-interaction correction because the long-range form of the potential is incorrect. So let's take another example. It's a charge transfer in a molecule that's made of a phenyl group and a pyrrole group. And let's say we want to do an excitation that moves the electron from one side to another. So here in the HOMO, the electron is on a chiral group, and if we excite to what looks like a HOMO to LUMO transition, we would get it mainly here on the phenyl group. So it's a charge transfer excitation from right to left. Now, when we do the calculation of the ground state, so then we get these these orbital energies here, and it looks like, yeah, it's a HOMO-LUMO transition, but if we now just take an electron from this orbital and stick it there and freeze those two orbitals, relax everything else, turns out we have 7 negative eigenvalues of the Hessian, and that means it looks like a 7th order saddle point. Okay, and we try that, and we try 6, and we try 8. Okay, we don't know quite what it's going to be. It turns out to be a 6th order saddle point. And you can see, in a sense, how it is. You see, the energy of the orbitals changes so much when you have a charge transfer excitation like this, because now the effective field for the other electrons is changed a lot. One of the electrons has moved so much. So you can see how much the orbital energies change from the ground state to the excited state. And now we have an unoccupied orbital here, and so we can just count, you know, how many ways are there for the electron in this spin channel to go down? You can see there's 1, 2, 3, 4, 5, 6. There's 6 ways for the system to lower its energy by occupying lower energy orbitals, so it's a 6th order saddle point. Now, this is calculation that gives an energy, excitation energy of 5.39 with just the PPE functional. And the best estimate by T2, you know, Pierre François Luz in Toulouse, and co-workers is 5.58. So it's a very big calculation. It's a, you know, big and complicated calculation than we get with a simple PPE functional. And the functional, the computational effort here is very similar to a ground state calculation, really. All right, so how is this implemented? I must say right away, I am a real fan of VASP, and I'm a VASP user. I got license 46. This is one of the first VASP licenses, right? 46. Yeah, who were these 45 people before me? Must have been just locals, you know. Anyway. But we work with this GPOC code, actually, when we do our sort of development, you know. And then I go and visit Georg once in a while, and I try to convince him to implement this in VASP. But this is also now the default time-independent DFT calculation of excited states in Orca. So, no, I'm not going to go through this, really. This is just methodology. We can talk about this at the bar, right? Let's get to an application, interesting application. So this is the nitrogen vacancy defect in diamond. You take out one of the carbon atoms, you put in a nitrogen atom here instead, and then there's a vacancy right next to it. And it's actually negatively charged, so we have now 4 electrons here that are sort of in the gap, forming states within the gap. And what is known experimentally is that one can prepare a pure spin state here in an optical cycle. So you have a triplet state ground state here, and there will be you know, different sublevels of the triplet, you know, m equals 0 and plus minus 1. And then one can excite to a triplet state. There will be some chance of intersystem crossing to an excited singlet state, and then that singlet excited state comes to a singlet ground state. And then as this system comes from the singlet state to the triplet, it only comes into the m equal to 0 sublevel. So that by going through that cycle several times, you prepare purely m equal to 0 ground state. And since this is in the gap, in this very rigid lattice of diamond, this is long-lived and can be used for quantum technologies. Anyway, of course, there could be many other such you know, important defect states in some other materials. It would be nice to use calculations to screen and get to identify what other states might be even better than the NV-centered diamond. The NV-centered diamond was very interesting. Why do people know so much about it? It's a way to discriminate, you know, synthetic diamonds from natural diamonds. That's why the interest started, right? But it so happens to be an interesting thing for quantum technology too. But okay, so what's out there that we don't know about and could find out by doing calculations? Well, what calculations can be done to identify this? So here are calculations that were done by my former student Alexei Ivanov. He actually now works at a quantum computing company in Cambridge, River Lane. And so these are calculations, simple basic calculations with plane waves and so forth. We can see that the experimental value of the band gap is 5.5 eV, and of course PBE doesn't get that, and even R2 scan. But if you go to HSE06 or self-interaction corrected PBE, you get the right band gap. And I'm going to show you HSE06 calculation. We're working on self-interaction calculations, but we haven't got them done yet. So you have 3 states in the gap, and you have 4 electrons to arrange there. And so we calculate these basically single determinant states separately, but then actually we need to so that's the ground state here, and then we have the open cell singlet and so forth. Then we need to actually construct the right wave function by group theory arguments and get the excited states. Also for the open cell singlets, we have to calculate both the mixed singlet state and the triplet state and do so-called spin purification. Let me not get into that in detail, but this is what we get for the 4 states, the ground state, the ground singlet, the excited singlet, and the excited triplet. It does depend quite strongly on the functional you use, as you can see, especially for the singlet excited state. And here we have R2 scan and we have HSC. The experiment is pretty close. I mean, with the HSC is giving us a 0.1 eV higher excitation energy for the triplet. But with the relaxation here in the excited state, it comes down to very similar energy as the excited singlet. And so we can see that's really good for intersystem crossing. You have the relaxed triplet here very close to the excited singlet. And the relaxation in the ground singlet is much smaller, 0.07 eV. And there are some indications of what the experimental measurements here, but it's hard to pin that down. But it seems to be in a pretty good correspondence with experiments, actually. So it seems, contrary to some statements in the literature, that DFT indeed can be used for these things, even rather simple functional as well, to R2 scan or the hybrid functional HSE. I can show you here some other calculations. So here is Julia Galli's embedded beyond RPA calculation, a much more heavy calculation for sure. And it agrees pretty well with the R2 scan. And perhaps you remember the HSC06 is a little bit here above, in fact. So those agree really quite well. So this is a very involved calculation. It's an embedding calculation beyond RPA. And whereas we're just doing plane wave calculations in a big box. There's nothing to it, really. There are several other calculations. They are basically up and down all over the place, really. Even DW calculations here, way overestimating the triplet state. Anyway, but HSC06 doesn't always work so great, actually. And I'm going to show you one example of that. Here's a system where a lithium atom has been replaced, is replacing one of the magnesium atoms in MgO. And it's well known. So what ends up doing then, you see the lithium atom cannot deliver 4 electrons. It only delivers 3. And so we have an oxygen atom here that is hungry, and there's a hole sitting on the oxygen atom here. This has been studied very heavily, even in the 70s, with EPR and other techniques. And basically what people have come out to say is that there's a defect level here corresponding to this empty p state, really, about 2 eV or 1.8 eV above the valence band. Here's the band gap of 7.8 eV. And then there is one bond. You see, the hole is sitting on one of the oxygen neighbors of the lithium atom, not on all of them. And only one of the lithium oxygen bonds is lengthened by 14%. That's what people know from spin resonance measurements. All right? So what happens if you do a calculation with PBE? Well, of course, the band gap is way down, and the defect state is just in the top of the valence band. Okay, so that's what you would perhaps expect. We have very similar results for aluminum substitutional defect in alpha quartz. Similar kind of a defect, similar problems. The thing is that with HSC06, you don't get localization of the spin density on one of the oxygen neighbors, but it's distributed over all 6. And that is in strong disagreement with the experiments. Of course, the band gap isn't quite right either, but anyway. And the defect level is only 0.4 eV above the valence band. So really, it's not really in good correspondence. And then some people have actually questioned whether the experiments are interpreted correctly, since it doesn't agree with HSC06. Now, if you do the self-interaction correction, you actually get this very well. And you get the right band gap, you get defect level 2.1 eV above. But, you know, I would like to discuss, I don't know, you know, what people see the fluorescence basically from this and judge from that where the defect state is sitting. That does not mean that that's the energy of the excited state. We're still trying to calculate the excited state for this. This is just the orbital energy. Is that really the excited state energy? There can be a difference there, you know. But anyway, the spin density is localized here in the ground state on a single oxygen atom. Now, another interesting application is Rydberg states of molecules because they are very diffuse. A Rydberg state basically, if you look at all the Rydberg states, they sort of follow a sequence that is the Rydberg sequence, now just like the hydrogen atom, but you know they're slightly different, you know, effective charge, and that's because they're so diffuse that they just see a +1 charge of the remaining ion, you know. And so they're hard to get because when you do calculations with atomic basis sets, they're too confined. And then these Rydberg states tend to be too high in energy. So here's an example of ammonia. This is the HOMO, but then the Rydberg state is you know, much more delocalized, especially here the 3PZ Rydberg state. So Alec was a master student. He did benzo calculations, and he showed that even with PBE, you could get the Rydberg states to within 0.2 eV with this you know, time-independent saddle point search method. But with the self-interaction correction, you could get you know, much better agreement because with the self-interaction correction, you get the right long-range form of the potential. And that's very important when you have a very high delocalization of the electrons. But there was one state that really particularly bothered us. That was the 3PZ state of ammonia because this is the extrapolated full CI calculation from Toulouse. And it's off by 1 eV as compared with the PBE calculation, the self-interaction corrected calculation, or the experiment. And we believe this is because the atomic basis set is just way too narrow. It just confines the Rydberg electron too much. But how do we prove that? So we started to do calculations, and this came out of other issues too, of basically configuration interaction with neural networks to speed things up. So and this just got published earlier this year in a collaboration with Philip Hansmann and in Erlangen. So look, you've seen these kinds of things all the time, right? You run into this all the time. Yeah. Identify all the crosswalks. Someone told me that this is being done only because people are wanting to train neural networks. You know, this is used as input in training neural networks, right? Well, what goes into a configuration interaction calculation? Basically, you take the Hartree-Fock slate determinant, right? And then you do all the excitations. You do excite, and full CI means that you generate all the slate determinants you can possibly generate from the base set that you're using, right? So here's the other question. What slate determinants here are important for the ground state? Identify the ones that are important, right? So that's basically what convolutional neural networks are trained to do. The convolutional neural networks, they are trained to identify patterns in images, all right? And so yes, here's an example. You know, which one is a muffin? Oops, and which one is a chihuahua? What is going on? Huh? Okay. Yep. All right. Okay. So these are convolutional neural networks, and basically we apply them to these slate determinants. These slate determinants, these representations of the slate determinants are basically just ones and zeros, representing whether a molecular orbital is occupied with an electron spin up or spin down. And so here's an example. You know, here we have a slate determinant. This is the number of molecular orbitals. And the question is this slate determinant important or not? Shall we include it? And so what's done is, you know, you generate a pool of slate determinants, then take a random sample and do the CI calculation for that much smaller random sample, and then you train the network on that, and then you apply it. You decide, you know, you have some cutoff. You say, okay, I'm gonna keep these slate determinants. They have a rather large expansion coefficient, and I'll throw out the other ones, and then you can apply that to the full set of slate determinants. And that's basically how this works. We take some test samples of slate determinants and train the neural network on that. And so basically what happens is that for every slate determinant here for you know, spin up and spin down, the question is it going to be included or not? And the answer is either yes or no, depending on what the neural network says. So doing that kind of calculation, for instance, for the ammonia, we now get values that are much closer. But the key thing here is that we do the calculation of ammonia with plane waves. And we converge onto the excited state in the Hartree-Fock calculation. So we generate orbitals that are tailored to the excited state and have this diffuse orbital in there for the Rydberg state. And so it can converge then with 52 molecular orbitals into a pretty nice value. So I believe the extrapolated full CI calculations that are given much higher value by 1 eV are simply confining the Rydberg state by using atomic basis set rather than plane waves. I gave this talk in where were we in June in Wadok, and telling chemists, this is a chemist conference, we're doing calculations of molecules with plane waves. Sorry. Courageous. But for the Rydberg state, it's really the way to go. All right. So here's the Guinness World of Records CI calculation came from Fujitsu last year. 10 to the 12 slate determinants. So here, as you can see, the biggest CI calculation as a function of time, and here's this one by Gao and co-workers on propane, and they went up to 10 to the 12 slate determinants. We are doing this with neural network CI, and already with 10 to the 5 slate determinants, we're beating them. So the white line is the results of Gao. It's the correlation energy report by Gao, and then the blue is where we exceed them. We've gone beyond the correlation energy found by a full CI, by selective CI. So we have more orbitals, but much fewer slate determinants, 10 to the 5 instead of 10 to the 12. Now, using natural orbitals instead of the Hartree-Fock orbitals, one can get actually even more, the same number of slate determinants, even more correlation. All right, so where are we heading with this? So what we would like to do is to have very high-level calculations of molecules, let's say, reacting or adsorbing on surfaces with an embedding method, doing neural network CI for the critical region here, embedding that in DFT, and also not using a slab, but rather a reservoir here. That means that we are doing a semi-infinite solid rather than a slab. So that's the key. That's what we want to do, and we're working on this in different fronts. Let's see. So I still have 5 minutes or something like that, right, Gareth? So what about this? Yeah, this method. You see, most of the surface science calculations are done with a slab, so we have a vacuum on both sides. So it's in a sense a potential well that we're simulating here for the electrons. Whereas this other approach I'm talking about is you do first a calculation of the bulk crystal, and you basically get a green function representing the electrons there, and that defines the chemical potential of the electrons. And then you couple that to a slab indeed, but there's only vacuum on one side, or liquid, or whatever. So you have really a semi-infinite solid. This was actually a collaboration with the people in Denmark in the so-called Quantum Wise company that later got sold to Synopsys, a consulting company in the semiconductor business. So, but I still call them the Quantum Wise guys, and in particular Søren Smidstrup. And so this was published 2017, but it's really not being used very much. And Georg, are you going to implement this in WASP? Let's talk about it. Let's talk about it. It's let's see the difference here. So here's, for instance, if you calculate the work function of silver with ATK, which is the code from the Quantum Wise guys, you get this in a slab. You get these oscillations up and down. Also with WASP, of course. It's just the slab. The slab has this, sort of difficulty in converging to bulk results. Whereas if you do the semi-infinite solid, you get the blue line. Beautiful convergence. Let's look at the band gap of germanium near a surface. The bulk band gap is here. How big a slab do you need to get convergence inside the slab to the right band gap? You need actually 14 layers. Almost no one does a calculation with so many layers in a slab. you know. So these are always far from being converged, really. So, but if you do the semi-infinite calculation, you get the red line. It converges right away. So I think this is really. I just understand. I don't understand why we're not all doing this, and why didn't we start doing this 20 years ago? Tough coding. All right. So the key thing there with the ATK code is an atomic code, atomic basis set code. So it's easier to do the inversion and get the green function. So, but here we just do the linearization. We do Piping Messe linearization and then work with that. Okay. So then, of course, the solid-liquid interface is a big deal, right? In electrochemistry, photocatalysis. We have a liquid there, and we're typically when we do the calculations with on CO2 electrochemical reduction, we have basically an implicit solvent, except for perhaps 4 or 5 water molecules explicitly. It's really or we do an ice bilayer to represent the liquid aqueous solution. It's really crazy. I mean, it's really a mind-blowingly simple approach, but one really needs to have a proper representation here of the liquid. So we develop a polarisable potential based on basically multiple expansion. So we just do the dipole, quadrupole, octupole, hexadecapole expansion of the electrostatics and have as few parameters. We have basically 5 fitting parameters to the repulsive part, and mainly actually the damping functions in the expansions of the polarizability and the permanent multipoles. And then we get a function here for the interaction of between water molecules that we tailor to the DFT functional we want to use. So we dumb it down. We're not trying to get the potential function that best describes water. If we're going to use PBE in the calculations here in the QM region, we want PBE water. The last thing you want in a QMMM calculation is inconsistencies at the interface. And then we have another version of the potential here with the hybrid in whatever we choose, So that's the key thing for getting these things to work out. Okay. Well, look, I think I'm out of time, and I'm just going to show you here. This is from on top. We are actually on top of the volcano there that I mentioned to you in the beginning. So here's Alexei Ivanov, has been really absolutely fantastic in developing the methodology for and implementing this whole thing. Benny just graduated last December and excited, molecules in solution. I didn't mention that here. And then Elvar Jonsson is a long-time collaborator and is now a research associate professor at the University of Iceland, and really is in charge of the development of many of these things. Gianluca was a postdoc and then became independent and now got an ERC starting grant and has already moved actually to Trieste, University of Trieste. And he was really the one who got us into excited states and very, very successfully. Now, other collaborators are Jorik, who was a PhD student. He's now working with Frank Nese and Orca headquarters. Alec was a master student, now working with Mikhail Stabmatakis in Oxford. And then there's the group in Erlangen, and that's Professor Philip Hansman, who is spending a lot of time in Iceland. You can see he's wearing an Icelandic sweater, and you have the glaciers here in the back. And in fact, we have a joint student here, Louis Thirion, who is getting his PhD from both universities, and Max, a master student who is actually now in Iceland. And so that's the neural network part of the talk here is all done in collaboration with Philip and his group. And Paulo is at the Max Planck Institute there, working on atoms and excited states. So let me just flash here these conclusions, and I won't go through it. I'll just leave them here if you like to see them. So, but this picture was taken on top of the almost on top of the volcano there at around midnight, actually, in late July. And you can see we stayed up there for an hour. We could watch both the sunset and the sunrise. All right, thank you very much. I'll be happy to answer questions.